Hello everyone. So today I am going over an integrated 3B chapter 4 quiz review. This is over sections 4.1 to 4.3. So in the first problem, you are given a number n and you're given an a, and you're asked to find the indicated real nth roots. So they have to be real numbers, they're not going to be imaginary numbers. So n is the root, and a is what you're taking the root of, which will be in the radicand. So when I rewrite this, I'm going to write the 3 here. That's my root. Let me zoom in so we can see this better. So 3 will be my root. My radicand is negative 126. So keep in mind you can take a negative number to an odd root. You just cannot take a negative number to an even root. And an odd root has only one root. So the only number that you can take to the third power, so if you're trying to figure out, well, what number could I take to the third power, that's going to equal a negative 216. So the only number that you can take to the third power that would be a negative 216, I believe, is negative 6. So you can either guess and check and try taking different numbers to the third power to see which one works, and if you take 206 or 6 to the third power, you do get 216. The other way to do that in your calculator, if you don't know these off the top of your head, you can put the 3 in first. If you have a calculator like mine, you would put the 3 in first, and then you'd hit second and then the caret button so that it says X root, and then the 216. Now, will it do negative 216? Yes, it does. Okay, so it will take the odd root to a negative number. So negative 6, again, is your only root or the only cubed root for negative 216. All right, so that's the answer to number 1. Number 2, now our root is even. So when it's even, you have to remember that you're going to have 2 roots. 4 is what's going to go in your index, and then 1 is what you're taking the 4th root of. So that's your radicand. So there are actually 2 numbers that you can take to the 4th power that would equal 1, and that would be your positive and or negative 1. So an even root is going to have, when you're finding the nth root of a number and you have an even root, there will be a positive and a negative root. Okay, so in the next section, we are asked to evaluate. So when you're evaluating the expression without using a calculator, you want to start with the root. So these are numbers that you should show how step by step you could do this without a calculator. So the first thing would be to rewrite this in radical form. The 2 is your root. You don't have to put the 2. The 2 is the unwritten root. And then the radicand, or the base, is 49. The power, which is 1, we really don't need, because when you take something to the first power, it's not going to change it. But this, you always want to simplify the root, then take it to the power, because you want your number to get smaller before it gets bigger. So the square root of 49 is 7, and then if we take 7 to the first power, it's still just 7. Now, some of you might be thinking, well, it's an even root, so do I need the positive and negative? No. When you are evaluating, you only use whatever the sign is that's in there. So if this is positive, it's positive. This is positive, positive. If this was maybe a negative number, then you would make it negative. But only when you're finding, so this is kind of like an equation here. You're finding the nth roots of certain numbers. When you're evaluating, it's just whatever number you're given, whatever sign you're given, that's the root, or that's the sign that you're going to have when you after you've evaluated it. All right, long explanation for some too much. All right, so the next one here, 243, is a little bit bigger of a number. So, but even without a calculator, I want to see that you've taken the 5th root of the 243 first. You do not want to take 243 to the third power. That's something you wouldn't do without a calculator. But the fifth root of 243 is 3. And if you're not sure, you can take 3 to the fifth power on your calculator just to double check that. And then you would take that 3 to the third power, which equals 27. So that's our simplified radical expression. Again, notice we take the root, so the root is the bottom number, and the power is the top number. So you always want to simplify the root first, then the power. Okay, and then one more practice problem here. We have a negative exponent. So when you have a negative exponent, what you would probably want to do first is make it 1 over 16 to the 1/4 power, so that the negative exponent becomes positive. So when you have a negative exponent, it does not mean a negative number. It just means you're going to put it as a fraction over 1. So once we move that over, we put that 16 to the 1/4 power in the denominator. Now it becomes positive. But we're not quite done. Now we want to simplify this denominator. So 16 to the 1/4 power is the same as the fourth root of 16 taken to the first power. So the fourth root of 16, you should know, is 2. And then if you take that 2 to the first power, that's not going to change anything. So your answer is just 1/2. So that's your simplified expression. Okay, now we have some equations. For equations, when you have an even root, you are going to have a positive and negative. So you're finding the real solutions of the equation. But again, it's real solutions, so we are not going to be having any imaginary numbers. And they're asking us to round your answer to 2 decimal places, or 2 significant digits, or the hundredths, whatever you want to call it, when appropriate. Okay, so when you have these expressions or these equations and you have something to the third power, so your variable's here and it's to the third power, you want to get that expression, that x to the third power, isolated. Where, just like this one over here, whatever's being taken to the third power, which is this x plus 4, is isolated. However, if there was something in front of it or something added or subtracted after it, you would want to move that and get rid of that first. So it only looks like a couple of these have a number in front that we have to divide first before we get rid of the power. But always get rid of your coefficients before you get rid of the power. So that 8 that's being multiplied, you're going to want to divide it so that you now have x to the third equals 4,096 divided by 8, 512. And then to get rid of the third power, you're going to take the third root of both sides of the equation. So that third root, and that cancels out the third power. And then you'd want to take the third root of 512, which I believe is 8, but let's see. 8 to the third power is 512. So once you start dealing with these numbers a lot, you're going to kind of remember them. But again, if you didn't know what number to the third power was 512, you could either put it in the calculator and guess and check, or put the 3 in first, hit the second caret button. So this means the third root of 512, hit your equals, and you'd get 8 that way. Now, because this is an odd root, there's only one root. It's not going to be positive or negative, it's just going to be 8. All right, so that is the answer to number 3A, our first equation. The second equation now, we have something in parentheses taken to the third power. So we cannot get rid of the 4 because it's part of that expression that's being taken to the third power. There's nothing in front, there's no coefficient in front that's being multiplied. So your first step is actually going to be to take the cubed root of both sides of the equation. So when we take the cubed root of this side of the equation, that's going to cancel out. and you get x plus 4 equals the cubed root of 21, which is not a perfect cube. I'm wondering if that was supposed to be 27. Well, I guess we're going to, it does say round to 2 decimal places when appropriate. Okay, so we're not going to do anything with that yet. We cannot simplify the cubed root of 21 because the only factors of 21 are 3 and 7, and you'd have to have something to the third power that would be a factor of 21. So we cannot simplify that. But we do want to get the x by itself, so I'm going to subtract 4 now. And since this is a radical, this is a whole number, you cannot combine them. They are not like terms, but we do have now the x by itself, and we can now plug this in the calculator as the cubed root of 21 minus 4. So make sure that that minus 4 is not underneath the radical. All right, so just like before, we're going to take the cubed root, so 3 second caret 21, and then minus 4. So this means you're going to take the cubed root of 21 and then subtract 4, and we're going to round it to 2 decimal places, or the hundredths place, which will give us negative 1.24. So x is approximately negative 1.24. And again, because it's an odd root, it's only a single root. There's only one solution, or one root of the cubed root of 21, not 2. So that's your answer for 3b. 3c, we've got another equation, but this time it's a 4th power. So to get rid of the 4th power, we're going to have to take the 4th root. Let's see, different color here. Let's try some purple. All right, so we're going to take the 4th root of this x minus 8 to the 4th and the 4th root of 81. Now, because it's a 4th root, there are 2 4th roots of 81. So in my next step, the left side simplifies to x minus 8, but on the right side, the 4th root of 81 is a positive and a negative 3. So a positive or negative 3. Those are both the roots of 81 because we have an even root. So in your next step, when you add 8, you're going to actually have 2 solutions. So when you're simplifying this, you're going to have x equals positive 3 minus 8, but you're also going to have x equals negative 3 minus 8. So that positive and negative 3, I'm going to separate, and then, I'm sorry, not minus, plus 8. Because we were subtracting it here, we add it here. So we're adding 8 to both of the positive 3 and the negative 3. So when you simplify the first one, you get 11, and then negative 3 plus 8 is 5. So x is going to equal 11, and then x is also going to equal 5. So you're going to have 2 solutions there. All right, so hopefully you'll remember to do the plus minus when you're taking an even root. The next problem is again an even root, but the 5 that's in front is a coefficient. We have to get rid of that 5 first. Then when we rewrite this, we will have x to the 6th power equals 30 divided by 5, which is 6. So now when we take, we want to separate these equation problems a little bit. Starting to run into each other. Okay, so to get rid of the 6th power, we need to take the 6th root of both sides of the equation. So when you take the 6th root of your x to the 6th, that leaves us with just x. But the 6th root of 6, because it's an even root, will have 2 solutions, the positive and the negative. 6 is not a perfect 6th power, so we are going to have to use our calculator to evaluate this. So in your calculator, start with your 6 and then second exponent, or second caret, so that the x root comes up, and then 6, hit your equals, and we're going to round to 2 decimal places. So 1.3, that 4 is going to become a 5. So 1.35. But again, it's positive or negative 1.35 because it was an even root. All right, so hopefully you will understand those equations. The next part is simplifying, or writing something in simplest form. So there were 3 conditions with simplest form. Number 1, you cannot have a radical in the denominator. Number 2, you cannot have a fraction under a radical. So you cannot have a radicand that's a fraction. So I don't see any of those in here. But then the last situation is that you cannot have a perfect nth power underneath the root. So as I'm looking at this number here, I'm thinking, well, it does 162 have a factor that is a perfect cube, like 8 or 27? And if it does, then we have to simplify it. So let's go back to A here, because in A, we have 2 terms in the denominator, where all the rest of these just basically have, if you have a denominator, it's only 1 term. So when you have 2 terms in the denominator, you and one of them has a radical, we're going to multiply it by its conjugate. And this conjugate, what's nice about it is it's going to, when we multiply this denominator by its conjugate, the radical is going to go away. So when you, the conjugate of 9 minus the square root of 6 is actually 9 plus the square root of 6. So it looks exactly the same, except your signs are opposite. But we have to do that to the top and the bottom, because technically we're multiplying by 1, and anything divided by itself is 1. So we're multiplying by something that's equivalent to 1 so that we can get the radical out of the denominator. So in the numerator, that 8 times that 9 will equal 72, and then the 8 times the square root of 6 will just be plus 8 square root of 6. So that's what your numerator is going to look like. The denominator is where we have the work, some work to do. So you basically have, so I'm going to do this off to the side, you basically have 2 binomials that you are multiplying together. So when you take the 9 times the 9, you get 81. 9 times the positive square root of 6 is positive 9 square root of 6. Notice you do not multiply those numbers together, because 9 is a whole number, 6 is a radical. Cannot multiply a rational with an irrational number together. And then on the inside, the negative square root of 6 times 9 is just going to be a minus 9 square root of 6. And then the last term, the negative times a positive, be careful with that sign. Negative times positive is negative. The square root of 6 times another square root of 6, you can either write it as the square root of 36, or you can write it as the square root of 6 squared. Now we're going to simplify. So the 81 we can't really do anything with, but this positive 9 square root of 6 and the negative 9 square root of 6 cancel out. And then your square root of 6 squared, that square root and square cancel each other out, but you still have a minus here, and then 6. So the 81 minus 6 is going to equal 75. So that becomes the denominator in your simplified expression. So that is our answer to 4A. 72 plus 8 square root of 6 over 75. All right, moving on to the next one, B. And I'm going to just kind of separate this so these problems don't all run into each other. So B, the problem I have here is that I have a radical in the denominator. Well, the only factor of 5 is 1 and 5. So we cannot simplify the cubed root of 5. But what we want to do is multiply by another cubed root so that we end up with a cubed root of 5 to the third. Because if we have a cubed root of 5 to the third power and the third root will cancel each other out, giving us a nice whole number. Well, if you look at what we're given so far, we have a 5 all by itself. So that is basically being taken to the first power. So in order for us to get a 5 to the third power, you have to multiply by a 5 squared. So the root has to be the same. They're both cubed roots, but if they're the same root, then you can multiply what's underneath. So 5 to the first times 5 to the second will give us 5 to the third. So that's how we figure out what to multiply this by. However, you cannot just multiply the denominator. You have to also multiply the numerator by the same thing so that it's equivalent to 1. And then again, because it is they're both cubed roots, you would multiply the numbers underneath together. 4 and 5 squared multiplied together will give us 100, but it's going to be a cubed root of 100. And then we're going to just do one more step, simplify that cubed root and that third power. So they cancel each other out. So our simplified form, or simplest form, would be cubed root of 100 at the top over 5 at the bottom. Now keep in mind, some of you might think, can't we reduce that? No, you cannot. Don't do it. This is a cubed root. This is a whole number. So they are not like terms. You cannot do anything to simplify that. So it's just cubed root of 100 over 5. And you're done. So again, there's no radical in the denominator, there's no fraction under the radical, and 100 does not have any factors that are perfect cubes. So those were the 3 conditions to be in simplest form. Okay, so now we're going to look at C. Well, in number C, we don't have the same base. We do have an exponent on the outside, and we've also got this exponent on the inside. So there's a couple different ways that you could do this. You could decide to multiply the exponent in right away, taking the negative 1/6 times the 6, and then because when you have an exponent outside of an exponent, they get multiplied. So we could do that, or we could try to reduce this first because they're both being taken to the 6th power. I could reduce this to 5/2 to the 6th power. So yeah, I think I'm going to do that. Maybe I'll just show both. All right, so because they're both taken to the same power, I could rewrite this as 10/4 to the 6th power. But don't forget, you still have that whole thing being taken to the negative 1/6 power. So then I can reduce the 10 over 4 to 5/2, and I can multiply my exponents here at the same time. So the 6 times the negative 1/6 is just going to be negative 1. Okay, so when you have a fraction taken to the negative 1st power, to simplify it, you basically would just take the inverse of it, or the reciprocal of it. You could write it as a 1 over 5/2, but then you'd have to simplify that. So the easiest thing to do when you have a number to the negative exponent, especially if it's negative 1, you just flip the expression. So the 5 would go at the top, or the 5 would go at the bottom, and the 2 would go at the top. And so now the exponent would be positive. And that would be your simplified form. All right, well, let's say you don't like that explanation. Well, let's try it another way. So let's say we multiply the exponents on the outside. Oops, I forgot those exponents. So if I distribute the exponent of negative 1/6 to my numerator and denominator first, that would then be 10 to the negative 1st power over 4 to the negative 1st power. Well, because you have a negative exponent, to make it positive, you have to move it from the top to the bottom or the bottom to the top. So if I move this 10 to the denominator, it becomes positive 1 for my exponent. When I move the 4 to the negative 1st power to the top, it's going to become 4 to the 1st power. So that, and then now we can reduce anything to the 1st power is itself, but I can reduce the 4 over 10 to 2/5. So that's maybe just another way of working out the problem. But again, we end up with the same result and the same simplified answer in the long run. Okay, let's move on to the next problem here. Letter D. We have, now this one actually 42 and 6 can divide evenly, and since they're both being taken to the 1/4 power, I could, like I did with the last one, put the 42 over 6 together to the 1/4 power. So this expression is equivalent to this expression, because if I distributed the exponent to both the numerator and denominator, that would give me what I started with. But you still have that exponent of 6 on the outside, so don't forget to bring that down. Now the 42 divided by 6 will give me 7, so that simplified nicely. It's still being taken to the 1/4 power, which then is being taken to the 6th power. Well, 7 is a prime number. It's not going to have any factors that are perfect 4th powers, so the 7 to the 1/4 power cannot be simplified. However, you can simplify this exponent. When you have an exponent outside of an exponent, you multiply them together. So if we multiply the 1/4 times 6, that's going to equal 6/4. However, you can reduce that fraction to 3/2. Still cannot reduce the 7. There are no perfect squares that are factors of 7. So 7 to the 3/2 power is your simplified form. Okay, moving right along. All right, so with letter E, you have 2 cubed roots being multiplied together. So you could start by multiplying these numbers underneath together, or you could start by factoring, because what we need is something to the 3rd power. That we need perfect cubes to simplify this. So 4 is not a perfect cube. However, 4 does factor into 2 times 2. And my 162 factors into 2 times 81. So when you have things that are perfect cubes, you can multiply these together. Well, the 2 times the 2 times that 2 then will be 2 to the 3rd power. So I would have a 2 to the 3rd power times 81. Now 81 we're going to simplify in just a second, but that cubed root of 2 to the 3rd now, since we have a perfect cube, the 2 can come outside. All right, so that 2 to the 3rd power was simplified and we get 2 on the outside. Well, 81, the factors of 81, if you don't know them off the top of your head, you can, off to the side, different color, take that 81 and factor it out. Well, it's not even, so I cannot divide it by 2, but I can divide it by 3, which gives me 27, which I can divide by 3 again, which gives me 9, which I can divide by 3 again, which gives me 3. So 81 is 3 to the 4th power. But I need a perfect cube. So instead of writing 81 as 3 to the 4th, it's better if you write it as 3 to the 3rd times 3 to the 1st. So it still equals 81, but what's nice now is the cubed root of the 3 to the 3rd will simplify, and we can take that 3 out, but this 3 is going to still be inside the radical. So your simplified value, or simplified form, the 2 and 3 can be multiplied together, which gives you 6, but the cubed root of 3 remains on the inside. So we do not have any perfect cubes that are factors of 3, so we're done. That one is simplified. All right, and then we have letter F here. So in letter F, we have 7, that is not a 7 to the 4th power. I know it looks a little confusing, but it's 7 times the 4th root of 567 plus 5 times the 4th root of 7. All right, so this is the first one that had a plus sign in between. When you're trying to add or subtract radicals, the radicand and the root have to be the same. Kind of like if you have to add like terms. You cannot add an x squared term with an x term because they're not like terms. Well, you cannot add a 4th root of 576 with the 4th root of 7. So my guess is that this 567 is going to have a perfect 4th power a factor of it that's a perfect fourth power. And I'm guessing that the other factor is going to be 7. So let's try taking 567 divided by 7 and see what we get. We get 81. And earlier, in the last problem, we said that 81 was 3 to the 4th power, so 81 is a perfect 4th power. So what we're going to do here is we're going to take that 4th root of 567 and we're going to factor it into 81 times 7. And then I can bring the second term down. And then the 4th root of 81 is 3, so that 7 that's already on the outside, we're going to multiply 3 with it because the 4th root of 81 is 3, but the 4th root of 7 has to stay underneath. So we're going to get 21 4th root of 7 plus 5 4th root of 7. So now we have like radicals. Just like if we had 21x plus 5x, we would add the coefficients. Well, you're going to do the same thing here. You're going to add the coefficients to get 26 4th root of 7. So that is our simplified answer. All right, moving on to page 2. So in page 2 now, we're still writing these things in simplest form. However, we're going to assume that all variables are positive, which means we do not have to worry about the absolute value that we had talked about in the last lesson. So we're just going to simplify these and not worry about absolute values of things. We're assuming all of our variables are positive. Okay, so here we have in problem A 6th root, and we've got 64, we've got r to the 25th, we've got s to the 18th, and t to the 17th. So once again, you cannot, when you're simplifying radicals, if you have a 6th root, you need the only way you can simplify it is if you have something to the 6th power. So 64, I think, is 2 to the 6th power, but let's try. Take 2 caret 6, and we do get 64. So I can rewrite that 64 as 2 to the 6th power. So I'm not changing the value, I'm just changing the way it looks. Now the r to the 25th power, I'm going to need an exponent here that can divide can be divided by 6 evenly. Well, 25 cannot be divided by 6 evenly. However, if I separate that or factor the r to the 25th into r to the 24th times r to the 1st, now the 24 can be divided by the 6th. So r to the 24th power is a perfect 6th power because it's basically r to the 4th taken to the 6th power. But this r to the 1st is going to be kind of left over. All right, your s is next. Well, 18 can be divided by 3 evenly, so we're going to just leave that alone. That one does not we don't have to do anything creative with that one. And then t to the 17th power. Well, 17 cannot be divided by 6 evenly, but how many times does 6 go into 17? Twice. So that's going to be t to the 12th. So you can, because 12 divided by 6 goes in evenly, and t to the 12th times t to the 5th will equal that t to the 17th. So now that we've got everything factored into our perfect 6th powers and our leftovers that are not going to be perfect 6th powers, we can start simplifying. So the 6th root, so this one is a perfect 6th power, this one is a perfect 6th power, this one is a perfect 6th power, and so is that one. So the 6th root of 2 to the 6th is 2. So that's going to go on the outside of the radical. The 6th root of r to the 24th, just divide 24 by 6, and you get r to the 4th. Then I'm going to go to the s to the 18th. The 6th root of that, take your 18 divided by 6, and you get s to the 3rd. And then you can divide the 12 by the 6, and you get t squared. and then you've got your leftovers that still have to stay under that 6th root of r t to the 5th. And there we have it. So all of these reduced, and they came on the outside, and then the r and the t to the 5th had to stay underneath, and that's our simplified form. All right, moving on to B. So in letter B, we have something similar to what we had on the last page. You have an m to the 1st power under a cubed root. Well, we cannot have a radical in the denominator, so we're going to have to multiply it by another cubed root so that we get the cubed root of m to the 3rd underneath, so that the 3rd root and the 3rd power will cancel out. Well, if you have m to the 1st, you need to multiply that by m squared. So still have to have the same root, but the m to the 1st times the m squared will give you m to the 3rd, so that those will cancel out. So that's how I figure out what to multiply by. But you have to do it to the numerator as well as the denominator. So whatever you do to the bottom, you have to do the top, because this has to equal 1. So in your numerator now, we have now the 5th root of 243. Every once in a while you might get something that's a perfect power, or that can be simplified. So let's just try that. I believe that 3 to the 5th power is 243. So let's see, 3 to the 5th power is 243. Well, again, I've been using a lot of these numbers for a long time, so I'm familiar with them. But if you didn't know off the top of your head, you're going to take your 5, put it in the calculator first, and then to take the 5th root, you hit second and caret. So this means the 5th root of 243, and then hit your equals, and you'll find out that it is 3. So that 5th root of 243 is 3, but the 3rd root of m squared just is going to go next to it. We can't do anything else with it. And then in our denominator now we have the cubed root of m to the 3rd. So the cubed root and the 3rd power cancel out. So our simplified answer is 3 cubed root of m squared over m. Sorry, didn't need me to move that over. So notice that the m here and the m squared cannot be reduced, because this one is under a cubed root where this one is not. So they are not like radicals. They cannot be simplified. So this is as far as you can go. Simplified form. Okay, now the next one is a little bit tricky. We're going to have to be creative with this one. The first part of this is not that hard. So your 8th root of n to the 8th, we could factor that into the 8th root of n to the 8th times the 8th root of q squared, factoring that n to the 8th and that q squared, and then the 8th root of n to the 8th would just become n. And then here we have this 8th root of q squared. Well, because 8 and 2 are both even, and they're both divisible by 2, you can actually reduce that. You could rewrite this as a rational exponent of 2 over 8, and then that 2/8 would reduce to 1/4. So that fraction could reduce to 1/4, and then q to the 1/4 power is equal to n to the 4th root of q. So this expression here, simplified, gives us n to the 4th times the 4th root of q. So now I'm going to bring my second term down, minus 8n 4th root of q. So if we had not simplified this 8th root of q squared, we would not be able to combine it with the 4th root of q here. So hopefully you could understand that my steps here, but these couple of steps in the middle, you could have just gone from here to this simplified version and reduced the 2 and the 8 to get 4 and 1, which the 1 is really insignificant. So the fourth root of q to the first is the same as the fourth root of q. All right, so let's look at what we have now. We have two terms with a fourth root of q in it, and then we have an n and we have a minus 8n. So these are like radicals. This n here basically has a coefficient of 1. So if you have 1n minus 8n, you're going to get a negative 7n. And then you still have that fourth root of q as the radical. So it's kind of like if you had 1x minus 8x, you would get negative 7x. Well, if you have 1n fourth root of q minus 8n fourth root of q, you get negative 7n fourth root of q. So just, it looks more complicated, but it's just like adding like terms. You add the coefficients, and our coefficient here is 1, and then our coefficient here is negative 8. So when we combine that, we get negative 7. All right, so that one's a little bit trickier. We have the same thing going on here, very similar. I'm going to rewrite this over here. So I'm going to factor the 125 and the p to the fourth into 125 times the p to the fourth. I'm going to rewrite as p to the third times p to the first. And why would I do that? Well, because my root is 3. And I know that I can simplify the p to the third with the third root. Now your 125, actually I probably could have rewritten that also. 125 is a perfect cube. It is equal, doesn't want to erase there, 125 is equal to 5 to the third power. So the 125 can be rewritten as 5 to the third power. The p to the fourth can be rewritten as p to the third times p to the first. Now this one over here can be simplified a little bit, just like the last problem. We have this 3p on the outside, but this 6 and this 2, the power and the root can be reduced. So if we rewrote it as a rational exponent, it would be 2 to the 6, p to the 2/6 power, which would reduce to p to the 1/3 power. And p to the 1/3 power is the same as the third root of p to the first power. So you don't have to rewrite it as a rational exponent and reduce. Hopefully you can just see it that this 2 and this 6, the power and the root, can be reduced. So this will be 3, and then this exponent would be a 1, which we do not need to write. Okay, but that's the second term. We still are not done with this first term. So I kind of was jumping ahead a little bit. So the third root of 5 to the third is 5. So because that was a perfect cube, it gets to go outside of the radical, or in front. The third root of p to the third is p. And then the third root of p to the first cannot be simplified. So now that we brought down our second term and we've simplified everything that we can, notice we have 3p cubed root of 3 plus, 5, I said 3, 5p cubed root of p plus 3p cubed root of p. So the p cubed root of p they have in common, which means we can add the exponents, or not exponents, we can add the coefficients, which gives us 8p cubed root of p. And that is our simplified version. All right, so be ready for one of those on your quiz. Next, we have a graphing problem. So when we look at the two graphing problems that we have on this page, number 6 is a square root, number 7 is a cubed root. The parent for the square root of x and the parent for the cubed root of x are a little bit different. It does tell us to graph both the function and its parent. So I'm going to start, I like to always start by graphing the parent, and I would recommend that you do the same. So with a square root, since it's an even root, your radicand, the number underneath, cannot be negative, or else you're going to get an imaginary number. So the parent table, if you make a parent table, you cannot use -2, -1, 0, 1, 2. You can't use -1, 0, 1. But you can use 0 and 1. You just can't use the negative values. And then the next number that I would want to plug in, instead of 2, I'm going to go to 4. Because what am I doing with these x values in the first place? I'm substituting them in for x, and I'm taking the square root of them. So if I substitute 4, which is a perfect square, the square root of 4 becomes a nice whole number 2, which makes it easier to graph. The square root of 0 is 0, the square root of 1 is 1. So these are the 3 points that I'm going to graph for my parent. 0, 0, 1, 1, 4, 2. So, and I'm going to make it a dashed graph. So this is my parent. All right, so the next thing we're going to graph is the g of x. So if you look at the difference between these two functions, we have this +1 under the radical and this +2 after the radical. Well, with transformations, with other functions like the quadratic and the absolute value, when you have a +1 in parentheses or inside the absolute value or inside the radical with the x, that tells you that your h value is -1, and it's going to be moving the graph. It makes the graph move to the left 1 space. And down here we have to do a description, which we'll do that also. However, anything on the outside that's being added or subtracted at the end, we usually identify that with as your k value. And notice that when this is +1, the h value is actually the opposite sign. Hopefully you remembered that. And then, but your k, anything on the outside, stays the same. So think inside opposite, outside same. So when k is 2, this number at the end that's being added or subtracted makes it the graph move up or down. So this is going to move it up 2. It's also going to change your starting point. Instead of your starting point being 0, 0, your starting point is going to be -1, 2. So -1, 2 is going to be our starting point. So you could, if you would prefer, you could add h to the x coordinates and add k to the y coordinates. So that would look like you would be adding a -1 to each of the x coordinates, and you would be adding 2 to each of the y coordinates, which would then give you the coordinates for your g of x function. -1 plus 0 would be -1, -1 plus 1 is 0, -1 plus 4 is 3, 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4. So these points you could graph now, which you can see I still have the -1, 2 now is in my table. Or you could just simply take each of these points that you had in the beginning. If you know that you have to move to the left 1 and up 2, this point, move to the left 1 and up 2 is right there. This point, move to the left 1 and up 2 is right here, which is the point 0, 3. If I take this point to the left 1 and up 2, that puts me here, which is the point 3, 4. So the points, the graph, and the description all kind of go together. Now, what if you're still not sure that these points are correct? Well, you could take these x values, or you could take them from here, and plug them into your g of x function. So -1 plus 1 would equal 0. The square root of 0 is 0, plus 2 does give me 2. If I substitute 0, 0 plus 1 is 1, the square root of 1 is 1, plus 2 does give me 3. If I put 3 in for x, 3 plus 1 is 4, the square root of it would be 2, plus 2 does equal 4. So again, the table, the graph, the equation, they all match up, which nicely. And we're going to label this as G. So this was our parent, and this is G. As far as our description, so since we went to the left 1, we would say that was a horizontal translation to the left 1 unit. And a vertical translation completely off the paper yet. A vertical translation up 2 units. Okay, so now domain and range. So domain is your x values or your input values. Range is your y values. So if we look at our starting point, which is our hk, -1, 2, the -1 is your x coordinate, the 2 is your y coordinate. So this starting point is the point that's the farthest to the left. So the smallest number that we can substitute for x is -1. And then the graph keeps going to the right forever and ever. So you can substitute values for x that are anything to the right of -1, including -1, but not anything to the left of -1, because that would make us get a negative number under the radical or under the square root, which then would be imaginary or undefined. So your domain is going to include -1, and it's going to be everything to the right of -1. So we're just going to simply say x has to be greater than or equal to -1. Your range is your y values. So if you look at the graph, the y coordinate for your starting point is 2, and then all of these points are going up from that. So the lowest y value is 2, so that's your smallest output value, and all the rest of these are going to have output values that are bigger. So your range is going to be 2, no, it's going to be y, all y values that are greater than or equal to 2. So that's how you do your domain and range. And there's our graph. Okay, the next one we have is our cubed root. So the first thing again I'm going to graph is my parent. But because it's an odd root, you can substitute the negative numbers. So when I create my parent, I'm going to substitute -1, 0, and +1. The cubed root of -1 is -1. The cubed root of 0 is 0, and the cubed root of 1 is 1. So my starting points for my cubed root are going to be -1, -1, 0, 0, +1, +1, which look like they're in a straight line. But because it's a cubed root, it's not going to have the same shape as a straight line. It's going to have an S curve in it. So it's going to kind of go up and then over, and it's going to keep increasing slowly as it goes to the right. And then on the opposite side, it's going to go down, again, that kind of like an S curve, and it's going to slowly be going down to the left. But these 3 points are the ones we want to focus on. Those are what we're starting with. All right, so that's our parent. So now let's look at g of x. So there's a lot going on here. We've got a negative in front, we've got a 3, and we've got this 2. So we're going to actually have 3 transformations going on. The -3 is your a value. So even though a is -3, it actually gives you 2 different transformations. The negative is a reflection over the x-axis, and then the 3 is a vertical stretch. So it's a stretch because the 3 is bigger than 1 by a factor of 3. And then we also have that -2 that's underneath. So because it's underneath the radical, it's being added or subtracted, it's going to be an h value. But remember, anything that's on the inside, think opposite. So instead of a -2, h is actually a +2, which means it is going to be going to the right 2. So it's going to be a horizontal translation right 2 units. So some of you might be really good at your transformations and be able to do this without a table, but I'm going to show it with the table, and then I will explain how the points could have been graphed without a table. So when you have your parent function, the a value always affects the y coordinate, and you always multiply by whatever a values you have. So if your a value is -3, we're going to multiply my y coordinates by -3. And that's going to do two things. It's going to make it reflect over the x-axis and stretch those y values by 3. Since my h is 2, we always add h to the x coordinates. So that's going to affect the x coordinates. So I'm going to add 2 to all of my x coordinates. So then my new table for g of x, just do my simple computation here. 2 plus -1 is 1. 2 plus 0 is 2. 2 plus 1 is 3. -1 times -3 is 3. 0 times anything is 0. 1 times -3 is -3. So you want to make sure that you double check all your calculations to make sure that these are right and everything matches up. So when I graph these points now, 1, 3 is right here. 0, 2 is right there. No, that's not the right point. That's 0, 2. I'm supposed to graph 2, 0, which is right here. And then 3, -3, which is right here. So again, it looks like the points are in a nice straight line. However, there's going to be an S-curve in here, kind of like this one had an S-curve. But notice your center point is a lot farther away from these two other points, where in your parent, the center point is only 1 up and 1 over from each of those points, where now your center point is 3 over 1, has a rate of change or ratio of 3 to 1, 3 to 1 on both ends. Okay, so when you're graphing this, it's going to kind of go up and curve to the left like that, and then we're going to have this, it's going to kind of go down here, connect with that point, and go to the right. So you can kind of look at those 3 points, and it does look like it's stretched, and by a factor of 3 it is shifted to the right too if we look at our center point. And if we look at the direction, this is going up to the right, down to the left, or this one's going up to the left and down to the right. So it's definitely reflected. So how could we have done this without a table? Okay, well, let's start with this point here. If I were to, first of all, reflect it over the x-axis, that would put it here. And then when we stretch away from, when it's a vertical stretch, you're stretching it away from the x-axis. So here's your x-axis. So this point is 1 space away from the x-axis. So to stretch it by a factor of 3, you'd have to go 3 spaces away, which would put us here. So step number 1, reflect. Step number 2, stretch. So instead of 1, it's 3 spaces away. And then move it to the right 2, which will put us right there. So that's how we get that point without a table. My second point, if I cannot, because it's on the x-axis, you cannot reflect it over the x-axis or stretch it away from the x-axis. It's just going to stay right where it's at. So really the only thing you can do with this point is move it to the right 2, and there we have it. Well, this point we can reflect over the x-axis, which puts us here. And then to stretch it away from the x-axis by a factor of 3, this point is 1 space away, but then when we stretch it, it would be 3 spaces away. So reflect and stretch, then to the right 2 puts us right there. So all of that's going on, and that matches everything in your equation. The other thing that you could do, if you want to double check, you could take the 1, 2, and 3, substitute them in this g of x function for x, and you should get 3, 0, and -3 for your y values. So that's just another way you can double check everything, plug and chug. All right, so as far as domain, what's nice about cubed root functions is domain and range is always all real numbers, unless it's some sort of story problem where there's limitations. But for this one, there are no limitations. It does keep going left and right forever and ever, and it goes up and down forever and ever. So both your domain and your range, you can either write out in words all real numbers or just use the symbol that represents all real numbers. But only for cubed roots, not for square roots. Okay, we are at almost an hour now. We've got 2 more problems to go, but each one has an A and a B. All right, so here is in number 7, instead of having you graph you're given the graph and you have to write the rule for the function, and we're calling it g, which is graphed below. So this is our starting point. You can see that's going to the left, and if we try to identify a few other good points, looks like this one, and that one are pretty good points there. So, and one thing that I did put in here is graph the parent function first, so that you can easily compare what it was and how it, what kind of changes happen from the parent to this new one. So hopefully you recognize that this is a square root function because it has a starting point and only goes in one direction, where this is going to be a cubed root function. It looks like its center point is right here, and then you've got a couple other good points right here and here. So this is a cubed root function, where this is a square root function. So your parent square root is at 0, 0, 1, 1, and 4, 2. So that's what we're starting with. This is our parent. So how do we get from here to there? Well, first of all, it looks like it has to flip over the x-axis. So if I reflected this over the x-axis, this point wouldn't move, this point would go here, and that point would go here. So this would just be your reflection over the, not x-axis, y-axis. So this would be your reflection over the y-axis. And then notice that all these points now look like they're going down 3 spaces. So those are the 2 transformations we have going on: a reflection over the y-axis and a translation 3 units down. And our parent function, f of x, or you can call it just y equals, is square root of x. So what kind of changes do we need to make to this equation to make it reflect over the y-axis and make it go down 3? Well, most of you know that to go down 3, you just put a minus 3 at the end. But what do we do to make it reflect over the y-axis? Well, this one's one that you have to remember. Since it's reflecting over the y-axis, the negative has to go inside the radical right in front of that x. So the negative is going to go inside the radical right next to that x rather than on the outside. If the negative was on the outside, it would be a reflection over the x-axis. When it's on the inside, it's a reflection over the y-axis. And then to make it shift down 3, we're going to put our minus 3. So that is our equation. And then again, if you wanted to, you could try plugging in the x values. So if I plugged in this coordinate, this point has an x value of 0. If I put 0 in here, negative 0 is still 0. The square root of 0 is still 0. Minus 3 is negative 3. So that would give me that point. This point has an x coordinate of negative 2. So if I took a negative 1. If I took a negative 1, that would become positive 1, which the square root of it is 1 again. Minus 3 is negative 2. So that does give me the point negative 1, negative 2. So those are different ways of checking your work if you're not real confident. All right, so the next one here, again, we're going to graph our parent. So the parent for the cubed root is cubed root of x. And if you need to make a table, the numbers that we substitute are negative 1, 0, and 1. And the cubed root of those are negative 1, 0, and 1. So we start out with negative 1, negative 1, 0, 0, 1, 1. But it's going to look like this with this x curve and then going that way. So if this was our parent, what had to happen for us to go from here to here? Well, your center point always is going to tell you your h and k. So this coordinates of this point are 0, 3. So your h is still 0, your k now is a positive 3 though. The center point to start with was at 0, 0. So the h value did not change, the k value did though. So you can assume that it's going to have a plus 3 at the end, so it went up 3. And then you can say actually a reflection over the x-axis and a reflection over the y-axis with a cubed root would result in the same graph. So there's actually 2 different ways that you could write this function. But if you like or prefer reflections over the x-axis rather than reflections over the y-axis, you could put the negative out front. So a reflection over the x-axis would put this point here. It would put this point here, which would kind of look like this. And then if you were to take these 3 points and just shift them up 3, that would give us our new points. So we have, that would be a reflection over the x-axis and shifted up 3. So the negative out front makes the graph reflect over the x-axis. Our starting function was cube root of x, but then to make it go up 3, your plus 3 has to be outside or at the end after the radical. So that's one way of writing your function. But the other way of writing it, you could see it as a reflection over the y-axis. So if I reflected this point over the y-axis, it would put me right here. If I reflected this point over the y-axis, it would put me right there, which gives me the same graph that I had when I reflected over the x-axis. And then we still would have to move up 3. So that part of the equation doesn't change. But you could write your equation like this, or you could have the negative on the inside with the x plus 3. Again, this only works with cubed root functions, not with the square root. So a reflection over the y-axis and a reflection over the x-axis would be completely different. With the square root, if we reflected over the x-axis, it would still be going, it would go down to the right though. It would not be going to the left. Okay, so those are your optional answers for 7b. Okay, and last but not least, we are writing a rule for G described by the transformations of the graph of f. All right, so G is a translation 1 unit right and 3 units down, followed by, so since we're doing followed by, I'm going to call this interim or this intermediate step, when I'm just going down or to the right 1 and down 3, I'm going to call my new function h of x. So h of x is a translation 1 unit to the right of f of x. So that would look like 1 unit to the right would mean that I have to change my x's, so this x becomes x minus 1. So this x actually has to be replaced with x minus 1. And then to go down 3, we're going to subtract 3 at the end of the function. All right, so now let's apply that. So the 2/3 in front is not going to be affected. And then you've got this 4th root. And then this x gets replaced with x minus 1. And then you have this plus 4 still underneath. And then you have a minus, you're going to put the minus 3 at the end. So again, notice this x became x minus 1. That moves it to the right. And then the minus 3 at the end makes it go down 3. We can now simplify what's in there. So the x minus 1 plus 4 is x plus 3. So this is what our equation would look like if we went to the right 1 and down 3. But now we have this followed by. So the followed by, we're going to apply to our h of x function. A vertical stretch by a factor of 3. So we're going to now take our h of x function and vertically stretch it. So this is our final step. So g of x, which is our final equation, is going to equal 3 vertical stretch by a factor of 3. The 3 gets multiplied in front of our function h of x. So we're going to take 3 times that h of x function. So the h of x function was 2/3 4th root x plus 3 minus 3. So notice this is what we had here, 2/3 times the 4th root of x plus 3 minus 3. Now this 3 that's out front does have to be distributed to both of these terms. Notice this whole thing is one term, because the 2/3 and the 4th root of x plus 3 are being multiplied together, this is all one term. So when you're distributing this 3, you're taking the 3 times this one term and the 3 times the negative 3. Well, the 3 times the 2/3 is just going to be 2 because the 3's would reduce. And then you'd have a 4th root of x plus 3. And then the 3 times the negative 3 would equal a negative 9. So that would be our final answer, g of x. All right, so one more time. To make this move to the right, we have to subtract 1. So you could even just take this, and if you know that to the right you have to do the opposite, so just take your 4 and subtract 1 from it and you get 3. And then 3 units down you have to subtract 3 at the end. And then when you're doing a vertical stretch or compression, you multiply that equation that you just had right here by whatever you're stretching or compressing by. But then you do have to distribute it to both pieces or terms in the equation. Okay, the next one is here. So this is the starting function that we have. It's not a parent function. It's f of x equals the square root of x minus 5. And they want us to reflect it over the x-axis, followed by, so I'm going to do the same thing. I'm going to call this intermediate one h of x. And it's a reflection over the x-axis. Well, what do I have to do to the function to make it reflect over the x-axis? I have to multiply it by negative 1. So you're taking negative 1 times f of x. So negative 1 times f of x, which equals square root of x minus 5. So notice we have two terms here. So that negative 1 does get distributed, which gives us negative square root of x plus 5 now. So that's our first step. So this f of x function with a reflection over the x-axis is now negative square root of x plus 5. Now we're going to do the followed by. So the second part, followed by a horizontal shrink by a factor of 1/2. Well, you have to remember when it's horizontal, it goes on the inside, and for the inside we have to think opposite. Well, shrinks and compressions are things that are getting multiplied. So we have to actually do the reciprocal. So when you shrink horizontally by a factor of 1/2, you're actually going to take that h function and you're going to put a 2 inside. So you have to take the reciprocal of 1/2 and multiply it by 2. The x coordinate by 2, or whatever the x is by 2 in your equation. So to get g of x, we have to replace the x with 2x. So in our h function, this x gets replaced with 2x. So g of x is going to equal negative, instead of x, to make it shrink horizontally by a factor of 1/2, we have to put a 2 in front of that x. And then the plus 5 is not affected. So again, notice that the x gets replaced with 2x, which is actually a horizontal shrink by a factor of 1/2. So that is our g of x function. And that is the end of our notes, or the end of our quiz review. Good luck studying for your quiz, and have a good afternoon.